Thank you all for coming. We're very fortunate today to have Dr. Graham Hubler, who's recently retired after 40-plus years of service at the Naval Research Laboratories, to speak with us today about sorting out the difference between fact and fiction in the anomalous heat effects that are being reported in materials. Graham, for many years, was the branch chief for material science at the Naval Research Laboratory, and as many of you know, the Naval Research Labs has been among the very top national laboratories for fundamental work on material science. So with that, it's really a delight to welcome you here, and we're very much looking forward to your talk.
Hey, thank you. Thank you, Rob. Thank you very much. It's a pleasure to be here. I think it's my third time I've been here, if I remember right. A couple of years ago at a workshop. Is this speaker on? Doesn't sound like it is.
It's coming right into
Oh, okay. All right. Okay. And yeah. So this is a new title for me, sorting out fact and fiction, and I retired, as Rob said, recently, which I guess can open me up to be more opinionated and not to have the official line. And I will talk about some new work, old work actually, that has not been reported due to let's say internal problems at the institution, but it's something that you should know about and help sort out this fact and fiction that I'm going to talk about. Now, a lot of great people who've been working on these projects with us over the years. There's David Knies and David Kidwell head up the scientific effort of this whole effort, and you couldn't imagine better people. Rob knows David Kidwell, who questions everything, and I have to say that Knies even questions Kidwell at times, so they're always going against each other and trying to figure out, okay, what did we do wrong, or to poke holes in what is going on. They're great physicists. Dawn's a chemist, Xu Fen's a thin film physicist. Jan Kucherov passed away in December 4. And I have to say that I hired Jan in 2005, 2006 from Eneco. He's one of the reasons I got back into this area, because I saw work he was doing there back in 1997 that really impressed me. And it took me over 10 years to get a program going, but at that time I decided I wanted to. And, but Jan, when he had worked on this area with Eneco in Utah. It's a company that was using it. And he said, I do not want to work on this anomalous heat effect more than 10% of the time. And so he came and worked on ballistics with me with the Marine Corps and made some terrific innovations there. But he said, you know, this project really it's so complicated, it's going to take a national program to figure this out. And that was his opinion at that time. And I really respect his opinion. You know, some of you know Imam in the group. These guys are contractors working in the group. Jinghao He is got his bachelor's at Tsinghua University in Beijing, and a very talented guy. Alex is a chemist. Lou is a theoretician who does a lot of DFT calculations and electronic engineering modeling. Mike Mielich got us involved in transmutation back in 2006, so I put him in here as far as that. And we work really nicely with this group in Italy, very talented, and one of the reasons we got into this area in the first place. So those are the actors. So I've already given the introduction. I have a one-slide overview of this field. I will talk about transmutation, and I will make an argument there's no definitive evidence for it. In the anomalous heat, I'll talk a little bit about the gas loading, a lot about the electrochemical. And in the summary, I'm going to say that this anomalous heat is not chemistry, in my opinion. Okay, so this is the one-slide summary of what I think is happening here. We'd start down in the lower corner. We have energy involved, implausibility to community. But this is material-dependent, low-energy nuclear cross-sections. This is born out of nucleosynthesis community, who is looking at trying to measure nuclear cross-sections at low energy. They find that you get up to 1,000 enhancement in the cross-section below 10 kilovolt bombarding energy. Personally, I don't think it's related to this area, but the people involved, many people involved in this area believe that all these are real They're all connected, and they're all the same thing. My opinion is this is probably not connected to these other bubbles that I'm talking about, and it's very interesting, but it's going to have an independent explanation. There's a low-rate MEV particle emission. These are not firmly established, a lot of sporadic results. We heard about one today. Orders of magnitude less than the energy needed to produce, to explain heat. And I'm not sure these are related at all. I think these might have an alternate explanation, may be related. Now, over here, the excess heat is what we are concentrating on in the work that I've been involved with, and nuclear transmutation. And I think the proof of nuclear transmutation is very suspect. So the people involved in this for 20 years, many of them believe all these are related, they're all real, it's all DD fusion probably. I do not. And I think this is where we want to concentrate our efforts. These experiments are very hard to do, for example. So are these. Okay, so that's my one-page summary of where this area is. Now, back 2006, 2007, actually Mike Mielich was responsible for getting us involved with Mitsubishi Heavy Industries, Iwamura, who published this very interesting paper in 2002. And it intrigued us. And what he did was he took this palladium sandwich. It's a palladium with some sandwich here of palladium, calcium oxide layers, and cesium on top right here. Put pressure in here, heated this up to about 70 C, vacuum on the other side, and just let it permeate for a week or so, or a couple of weeks, okay? He claimed he did these transmutations. The one of interest here was cesium to praseodymium. Praseodymium is not found very much in the environment, so we thought. And so this is the one we concentrated on. And we had an agreement with Mitsubishi, and it said, okay, send us some samples. We'll tell you if we can find praseodymium on your samples. So this, by the way, is his original paper data. It shows cesium on 2 different runs going down with time of permeation, praseodymium going up with time. He claims changing the cesium to praseodymium. Now this one thing that attracted us, this was a vacuum experiment, clean, you can use electronic microfabrication techniques, should be an easy thing to figure out. Okay, so we got this agreement, and in this particular foil, here's the area that was permeated by Mitsubishi, and there are holes. It's a membrane with holes in it. The palladium goes over the whole thing. So they did one of these runs, kept these, sent these 6 to us, and we looked with this with trace element accelerator mass spectroscopy and inductively coupled mass spectroscopy at NRL and said, okay, are you really making praseodymium? Because you can make mistakes looking for small amounts. He looked at it with XRF, or XPS. Well, we used our trace element accelerator mass spectrometer, which I won't go into, it's not so relevant to this conversation. Just say that in that system, we could do M over Q versus Q plots, pick up charge state information as well as mass, and you find praseodymium well separated here. This happened to be a standard, and we found it in this technique. I don't have the actual one where we found it for some reason, but this is very definitive if the praseodymium is there, and we found it on us, and we were quite shocked, actually. We thought he was making some trace element mistakes, but here we found it. So once that happened, we took a long time to get an international agreement together, and we went to Mitsubishi, they came to our labs, and we collaborated for about 2 years on this project. Okay, so the goal, we unexpectedly really found this praseodymium. We initiated this research agreement and systematically decide which of 4 possible explanations could explain this, where those explanations are: experimental error, contamination, novel concentration processes, collecting praseodymium simultaneously dispersing the cesium, nuclear process that adds 8 nuclear masses and 4 charges to cesium to make praseodymium, which seems quite far-fetched. Okay. So David Kidwell headed up this effort. Inductively coupled mass spectrometer. It was 18 months in development to try to get to the point where you can measure small amounts. Now, it turns out if you just take palladium and looking for something at parts per billion on the surface, you can't do it. There's just too much matrix there. So going through how to dilute that, selectively dilute the palladium without diluting the contaminant is tough. It took 18 months to develop this. A calibrated procedure to selectively dilute palladium so that you could then make measurements at these very small rates. And this was a tour de force, really, for David Kidwell. But here's some rare earths, for example. And these are actual measurements, the measurement accuracy ratioed, that we could get. He can get down here. Here is 1 part per billion. You can do praseodymium down to a couple of hundred parts per trillion sensitivity. I mean, this is really, really remarkable effort, and do it reproducibly. And so that had to be developed before you start then looking to see what goes on. And then what was done was you go in and you do 2 types of measurements. You take the entire palladium foil stock that you're doing, and you measure how much praseodymium was in there in the first place to see if it could be concentrated, right? And then you do extractions to look for something that might have been formed on the surface. You do an extraction where you do some acid, you remove about a micron of surface, and then you measure that. And those 2 procedures you develop. The other thing that was done was taking one of these procedures, and we sent these blind samples. Actually, Mitsubishi sent blind samples to us and to Toray, a company that does this in Japan. And here was the agreement between us down at these nanogram levels here of something in the solution. So we cross-validated our technique. Now, it turns out that praseodymium or rare earths aren't so rare after all. And if you look, there's environmental sources of it, and flints, mish metal, specialty glazes on ceramics, or phosphors in CRTs. Here, for example, is a flint, okay? And you see here, if you can't see it, this is lanthanum, cerium, praseodymium, neodymium isotopes of several different samples of flint. Now, another thing you can do is you look at $10 bills and you examine the $10 bills, and you see that there's parts per billion or more. Once you go to parts per billion sensitivity, you see everything, basically. You see everything. So there's plenty of rare earths on a $10 bill. Here is a human hair, actually David Kidwell's hair over a period of 5 or 6, 7 years. Here's the rare earth elements. You see them all in the hair down at parts per billion. So it's everywhere. So, okay. I don't know that experimental detail. So anyway, one thing, so we worked on this, and we worked on the environmental contamination, always kind of shows the same signature. None of the praseodymium we found contained this signature. So it was not environmental contamination. That's good. That's good. We also found no praseodymium in the stock material that was used to do these experiments. That's good. Now, so anyway, we this is kind of a long story. I'm trying to cut it short, but a number of samples were exchanged. So we found praseodymium on samples sent to NRL by MHI, extracted by them, but in much smaller amounts than they said. None of the MHI produced samples sent to NRL and prepared for ICP-MS by us contained praseodymium to less than a part per billion. That's where we took samples he ran, we did the extraction on the surface to try to find this. They did the extraction on the surface, sent it to us. We saw it in there, okay? So this was confusing. What's going on? They seem to be able to extract it and we can't. And so we went to MHI and did some more work, one of which was taking swipes at about 50 different places in the laboratory, contamination swipes, right? Contamination swipes. And two of them, there's a third, two of them turned up large amounts of praseodymium. And these happen to be balance scale 1, balance scale 2, where you weigh out pollutants and you weigh things out. Happens also to be a central point where a lot of things you've done in that laboratory kind of pass through that point, right? So it turns out that these are abundance of contaminants collated with praseodymium from those two wipes. And you see there's cesium, there's rubidium, barium-137, praseodymium, samarium-169, samariums, and strontium. Okay, so what I'm saying is where this praseodymium was found, you found these in that region were also in that swipe. Okay, so then what happened was the ICP-MS analysis by us of MHI extracted samples from 9 specimens. Analysis showed 3 samples with praseodymium V3 also contained samarium and excess barium, which are 2 of the co-located ones. And some did not, but they did. So when you see this, and remember, we could not extract it in our laboratory. We could not find the stuff in our laboratory, and they could. So the presence of praseodymium may have other explanations than the transmutation of cesium to praseodymium. And also, this shows if you really want to look for transmutation, it is really tough. It requires extraordinary amount of tedious work to prove transmutation. You have to, what David Kidwell, in every step to develop his stuff, every step you make, you take a little bit out and analyze it to see if you contaminated it in that step. And there might be 50 steps in doing all this thing, and you leave these samples behind. Did I contaminate? Did I contaminate? When you're worrying about parts per billion, it's really tough. So it really requires a lot of expensive work. Now, there's new results reported just a couple of weeks ago at ICCF by MHI and Toyota. I've examined them. This is my opinion now. I've examined them at this point, and I believe they are not definitive for converting praseodymium or cesium to praseodymium or a couple of the other ones. It's interesting that Toyota's gotten involved in a big way. They did a lot of work. And Mitsubishi is doing, Iwamura, again, picked the work back up, and we think it's possibly because of Fukushima. They're still looking for ways to convert isotopes, but anyway. So now, a little bit more, just a couple more slides on this. What about electrochemical experiments? This is one that's highly quoted by Miley, which he found in doing electrochemical work, a whole bunch of elements that he claims were transmutated in his electrochemical experiments that weren't there before. And this is one by Mizuno where he's using plasma electrolysis, where you have a plasma in the system of D2O, and XRF analysis. Here's before, afterward, he begins to pick up platinum, lead, and copper, and iron, and chrome, tin, titanium, and so on. And some of his parts in there are stainless steel. But anyway, they're using something like this to say, oh, I've got elements that are transmutated. And I sort of have one answer, like Bill Clinton said, mathematics. Well, I have... yeah, arithmetic. So this is an ICP-MS spectrum of 0.1 molar lithium OD, and here is the counts in a log scale, and here are the masses. There's everything in the lithium. It's hard to get a clean D2O. Some of this is real, most of it is just real elements. They're all in there when you go down to really small levels. If you look at, these are going down many orders of magnitude, but it's there. And many of these chemically will concentrate on your cathode when you start doing electrolysis. Some of this is also overlaps of isotopes and multiple charge states, which are problems with mass spectroscopy, but it's just very, very dirty. So, you know, by taking this and claiming I got transmutation, it just requires a tremendous amount of work to prove it, and this does not prove it at all. Okay, so this is my final slide on transmutation, but the proof of transmutation requires extraordinary care in the analysis of all materials and all handling steps. And while well-meaning, most reports of transmutation are not rigorous. This is my opinion now. Everyone in this area has their own opinions, and I would probably get slammed by people for saying this. So anyway, I believe that all reports of transmutation are suspect at this time. Now, helium-4 has been observed by several researchers. It's a difficult experiment. It's not replicated at very many labs because it's a difficult experiment. They're one-off experiments, mostly. And I think the proof of helium-4 ash is going to await reproducible megajoule heat production. The megajoule to try to get enough signal there to measure. And reproducible because to set this experiment up is time-consuming. If you only get this thing once in a while, it's tough to do all the statistics you need to do it. And I'll get a lot of heat for claiming that this is not definitive, okay, in the community. But many of us believe this in the group I've been working in.
Can I ask a question
Sure.
regarding your previous slide? So the electrolysis, no, actually one more thing. So what is the explanation that before they didn't find any of all these extraneous elements?
This is a cathode before and a cathode after they did generated a high voltage plasma in the electrolyte and did the electrolysis with a plasma instead of just a DC current.
It was never used as an electrode and therefore had no,
was
not able to collect selectively some of these things from the heat.
Well, that would be one explanation.
Thank you.
Right. Where are we? Okay, so now let's go to the heat and the ash. So now most of these slides, or some of these slides, come from very recently from the 17th International Conference on Cold Fusion on August 12th. Again, this is gas loading, and I'm going to not talk a lot about this. Now, some of you haven't seen this before, but what is done is you charge. You have a sample material in a chamber and a calorimeter. You charge it with gas, hydrogen. You measure any heat. You then pump it out and measure any heat. And you can alternate. You can do it with deuterium. You can do it with hydrogen. Now, if there's no isotope effect or chemical effects, then heat in should equal heat out, which is an internal control, and H2 should equal D2. Okay. What is found, what David found, and David Knies initiated this way of doing this experiment where you charge, let the gas in, measure the heat, and then pump it out and measure the heat out as a way of knowing what the physics is going on. And in this case, with hydrogen, here, this is the pressure, right? So you put the pressure in, pump it out. And this is the heat from the calorimeter. And it's about, in chemistry, minus 19 joules is exothermic. And then when you pump it back out, you integrate these two, and they're basically the same. That's what you would expect. This is very reproducible. Now let's put in deuterium. And with his special material, which I'll talk about in a minute, there's 56 joules coming in, 13 joules out, a 4-to-1 ratio. And this is what got our attention in the first place. So this effect has been transferred to a couple other groups, have identically reproduced it. And the interpretation as novel science is difficult because the amounts of heat are not large, but still not understood. Now, one thing that explains some of it is HD exchange. What these materials are is a zeolite with a palladium formed with about 1 nanometer palladium particles formed in the cages of the zeolite. And another fact not seen here is that if the particle size gets above about 2 nanometers, this difference disappears between the hydrogen and deuterium. It's only the small particles. So anyway, so the D comes in, dissociates, it D2 moving out in the matrix is slow, but D is fast. It exchanges with the HD, which is extrathermic, not very much, but it is. And so you then have a way of, you're converting H2O to D2O. Eventually that produces a little bit of heat. But this thing can go on and on. After the first one, this is just burning up oxides and so on, so you always ignore this one. You can repeat this over and over, and you still get very much the same amount of heat out. Okay? So this is not well understood. The HD exchange can be accounted for this much of it, but it's not a very big effect at this point. Now what makes this sort of thing interesting is, okay, is there a critical size? Why does it disappear? Does it disappear because of particle growth, which we think happens, or does it disappear because you used up the water? So we don't know at this point. Now, one of the this is kind of a summary slide that I just put together. And gas loading has mixed results, but it's a very interesting area still to pursue. Here is Cantwell from Cool Essence, who basically have taken our material like ours. And here's a summary from a paper they just published. The results of our gas loading experiments of palladium-infused aluminum powder are consistent with the excess heat produced being due to an HD exchange reaction showing that the origin of the excess heat is chemical. Brian Airhan from Massachusetts claims no heat. Hyoki of Toyota claims no heat in the zirconium system, which is Arata's system, one of the first people who showed that there's some kind of anomaly here. He showed that years ago in the zirconium system. Mitchell Schwartz of Jet Energy claims small amount of heat in this system, zirconium, not palladium. Kitamura of Kobe University claims small amount of heat in a palladium system. Kidwell still claiming that some of this heat in the palladium system is anomalous. Chalani now from INFM claims a large amount of heat in nickel-based system. And this is the only national lab type place that has come out and said, oh, there's some big amount of heat. Several others, including Piantelli at Siena, are claiming decent heat from nickel-based systems. Now, you can't hardly see this for some reason, but Rossi at Defkelion claim very large heat with Rossi and Defkelion, sorry. With nickel-based system, we show, I believe these claims are highly unlikely and are probably wrong. Now, what is not known is that twice NRL personnel took equipment and tried to measure the excess heat at Rossi, with Rossi, and in the first case could find nothing. In the second case came up with about maybe 5% of the excess heat that he claimed he was getting, taking our equipment there and looking at it, but it was still hard to determine whether or not that was the case. Now, even if it was a few percent, it was a few hundred milliwatts, and that would be great, but within what we were able to do, it was not 3 kilowatts that he claimed it was.
What does he have to say about your estimate?
He ignores us. And we can't come to his place anymore. Now, we went to Defkelion, I don't know if I'm pronouncing that right, with nuclear radiation equipment this spring, and could not measure anything coming out of his system. And even though I haven't seen it, but I'm told in some of his latest PR that he claims that our laboratory was there and measured radiation, and it wasn't us. But anyway, so we see no radiation in.
That you've been in Rossi lab and Defkelion?
Defkelion was gamma detectors, basically.
No, when have you visited?
March. I think it was this year. March. Other people have gone there, and we're really concerned about all the hype around this. And I hope that they have a system that works, but it doesn't it looks too much like fraud to me. But I probably shouldn't say that. But anyway, we're very worried about that. So anyway, in summary, the gas loading is mixed results. The results from many quarters suggest there is an anomaly here, and we should continue to push this until we find one way or the other what is going on here, I think, because it's an important problem. The only research institution claiming large heat is Chilani. This should be watched and duplicated. And just as another note, Cantwell at Coalescence and Ahern and Ann, our guys at NRL, have looked at hundreds, maybe thousands of nickel-based materials, and we haven't found any nickel-hydrogen type heat, anomalous heat yet. So it's very, very much in flux. Okay, so let's get now to the electrochemical work, which we started, and it may not, I'll repeat that here, but we got decent, or I was able to attract decent funding for this in late 2009, and able to support from a couple of federal agencies, and was able to support about 6 people for now 3.5 going on 4 years. So it's been a pretty well funded effort. When we began it, I thought, oh, we're going to figure this out in 2 years. And it took us 2 years to get a first result, for crying out loud, let alone figure out what it is. But anyway, it's a tough area, and it's brought a lot of scientists to their knees. Okay, so for those of you who might not know, we use the ENEA, the Vittorio Violante configuration of a Fleisch and Pons cell, which is 3 foils, a platinum foil, so the edges are facing out of the paper, palladium in between, the electrolytes lithium OD, lithium OH, and you electrolyze it, you evolve hydrogen and oxygen. It's a closed system, so these are recombined in this catalyst bed, and you have a calorimeter. And it seems straightforward. Now, what I'm going to talk about is how we started getting this effect with the addition of metals and metal salts, which seemed to shorten the time to see the effect, and the focus on palladium rhodium alloys, which we also found out during the program that was important, and the steps taken to confirm our results. So the bottom line is these large excess power are generated 10% of the time in these cathodes, and we have failed to disprove these results, so we are now saying this is a real effect as we see it in our laboratory. Now, these are the number of cathodes that were run in these time frames. And you can see there's 130, 40, 100, 70 or so. And the time frame is these 3 different modes. They kept improving things to try to figure out what was going on. And this was a Teflon cell, and this sealed. The catalyst is up in here, and there's no way to put anything in a cell in this case. So this goes on here, goes inside this nickel diffuser, and then goes inside this 4-position Hart calorimeter. Very, very nice calorimeter, which we're very confident of. The other one here, we introduced the ability to, with these syringes, to put additions into the cell. And then later, we were worried about these being possible shorts. In the diffuser, we lost the diffuser, put in polymer cells. This is all PEEK material, and so this is what is being used now. All similar geometries but different materials. And basically we have this biologic VSP is what we use here. And one of the things we added right at the start was what we call a high-end current measurement, because this supply will report the low-end current. We wanted to measure the current at the high end, make sure they'd agree, because if you had a short or something, that would pick it up that you're losing current somewhere. And we had very, very consistent results for about 24 months. Very consistent. Power in equals power out. We got nothing. Ran 120 to 130 cathodes and got nothing in this cell. And here, this shows you the stability of the system under current control. The stability of the system under constant power control, but generally the power in is the red line, or the blue line. The power out is the red line, and everything agreed. Okay. So then, here's an example. This is an example run over time power, And here is, yeah, power in is the blue, power out is the red, the residuals are the black. So we see we go one watt steps, step, up to 8 watts is generally what we do. This also gives you an institute calibration when you run it. And you see they agree very nicely. This is what we saw for 2 years and 120 cathodes. You subtract them, and this is the scale over here. You say within 10 milliwatts or so, there's just nothing going on here whatsoever. So then, about 2 years, a little less than 2 years, a year and a half ago, whatever it was, started adding things, mostly out of desperation. And here, what you see in this particular one is the added Raney nickel. Raney nickel is a catalyst developed in the 20s or 30s, the 1920s or 30s. It's nickel on alumina. And what happens is we got this. And I say, well, that's interesting. Now, if you look at it, it's not very exciting. It's 40 milliwatts out of, where are we, 8 watts. So that's a 1% or a few percent, less than a percent. But it's there, and you could see it every now and then. And so we thought, well, that's curious. 40 milliwatt excess power. But we didn't pay much attention to it. We said, well, that's promising, but it's just not very convincing. It's such a small number, even though our calorimetry would say it's real. And then, let's see, where are we here? And then we sent some of this stuff to ENEA, and they got a fairly big result out of doing what we said to do. This is 12% excess. That's pretty good. It lasted for quite a while. And so this is also seen in another lab. So we went to, at a meeting in Frascati, we eventually found out that older lots of palladium had only one source, Engelhart. And that was hard to track down because a vendor would buy it from Engelhart, put their name on it, and they might sell it to another one, put their name on it. But we finally realized that it was coming from this source. So ICP-MS showed different impurity profiles in the current lots. The older lots appeared to have been recycled palladium from catalytic converters, okay, and they had rhodium and platinum in them. And the current lots are much purer in these elements, but have zirconium, yttrium, hafnium. Likely this change in crucibles, and likely the rhodium prices and maybe platinum prices drove them to change the process and recover the rhodium and the platinum. And this was around the early 1980s. So you had, and so when we saw that, we can't find this material. So what we do, we started making our own alloys. So we started making palladium, rhodium alloys and the additions. Now here, this is just ICP-MS, just saying what I did, that the the detection of rhodium in the old lots and zirconium in the new lots. Okay, so what? This is the one we're still using. The very first one we ran, we added Raney nickel, cobalt, nickel sulfate here, and we got a result here, which is expanded. And you can see that here in the residuals, this thing suddenly produced over about 90 minutes 10 kilojoules of energy. And this is the kind of thing we were looking for. And we were still worried about, and we put in these additions. If you took those additions and oxidized them, you couldn't account. You would have to have 1.6 kilovolt per keV per molecule to explain that amount of energy coming out if you're burning up what we just added in. Okay, so there's other results. Here's another one. Okay, here's the residuals, adding the power in. Suddenly, and this is a nice bite. It's 2.4 kilojoules, and it's several watts of excess power. Just lasted for a little while. Okay, here's one where we added these guys in, and suddenly gives us 4 kilojoules, 100 milliwatts up in here. That's interesting. Here's one in which we have 11 kilojoules coming out. This one had a bunch of different changes trying to get things to go for us, and then added Raney nickel after. This is what we do every time, add these things in this order, and boom, you'll see this. And that's interesting. Let's take a look at another one. Here's one with 11 kilojoules, in which we tried different things, added the Raney nickel, and boom, you get out this result. Here's one with 1.2 kilojoules that you see after adding these things. Here's one with 4 different hits of 26, 30, 15, 13 kilojoules as we were ramping it up. Yeah.
Can you go back a slide?
Yeah.
Can I ask a question?
Yeah.
Are we just ignoring the fact that the negative areas, I mean, maybe there's good reason for ignoring that all those negative areas might add up to pretty close to some of the positive area that you're pointing out, but we're ignoring.
Okay, let me show you right here why that's okay. When you make a large step in the power, the calorimeter has 30-minute time constant, and the time constant of the power is right. So what you see is this deficit, okay? And now you recover that deficit when you turn things off. Now look, here's a case where we stepped it up, you see this. Here's we stepped it down, you get it back, okay? So you integrate those and you come out to 0. So if we step this down at the end, you will get that heat back, but it's an integration of time constant phenomena that's you can model it perfectly. This one is pretty impressive. Total energies are good. It comes in these steps. We don't know why it comes in these steps. And again, what we were worried about now is these are metal syringes, so we went then to change the cell design again to all peak, and these are polymer syringes in order to add things in situ. And we still get it. In fact, this one was probably our best result so far. Now, this answers 2 different questions of Steve Koonin and company. They say, oh, you stored up energy in, you're getting it back out. Well, this is the beginning of the experiment. If you subtract the difference in these 2 curves, you might get 10 joules or something. And here we're getting out huge amounts of current. So it's not that. And this one, as you can see here, there's a gain up to 40x. This one, in terms of gain, this one was really an impressive event. And we're still, at this point, wondering, well, is this real? Well, we totally eliminated shorts because not only did we get rid of the nickel diffuser out here, we got rid of the metal syringes that were going down in there that might have touched the cathode. So it's just not shorts. Okay.
And you did not add any?
We did not in this case, but next slide, well, we have another slide in the original presentation. The peak doesn't clean up very well. And so from run to run, some of the stuff you got is on the walls in there and surely dissolves in there. And that's one possible explanation of why we didn't add anything and got this. Okay. So another one of Steve Koonin's favorites is that, well, you guys are putting RF power into the cell and you don't know what the input power is. And that's okay. So what we did is we added another resistor on the bottom and put an RTD temperature probe on the resistors and calibrated these resistors. When DC current went through, what is the temperature? When any current went through, what is the temperature? Okay. And then did some more runs. And here's one here, for example. Okay, here we're going along. Here's another case, by the way, where the power went up and you see the imbalance. Take the power down, you get back this energy here. This started taking off at this point. Okay, P out. Well, first of all, the P in was changed. This is under. It's another story. We run under power control at times, and you see the power out starting to take off. Okay. Here's the residuals. It's going up. There's a lot of power there, 3 watts. Okay, power out, power in, power out. Okay, so up 70 kilojoules of heat in that one. So what happened?
What happened after the 60 hours?
It shut it down, trying to. You know, David always tries to do something. I'm sure he did something to try to figure out what was going on, and it just turned off. You know how that is. What's the, oh, the other thing, sorry about that, there's an internal temperature probe in the electrolyte. Okay, what did the internal temperature probe do right here? Well, it's following the power out, as you'd expect if the power was coming out of the calorimeter. Okay. Then what did the resistors do on the anode and the cathode? Well, let's look, here they are, they're following the current. And this is under power control, and it turns out the voltage increases, so it's another whole story. During these anomalous events, we have a voltage increase. But those resistors followed what the current was actually doing, which says the current is really measuring what it's supposed to, and we don't have RF getting into the system. Okay, so we have a number of them that have been instrumented this way. The equipment is working right. So you have to believe all of these things we're getting. The 70 kilojoules, there's this one here. We believe these are all this effect that we've been looking for. Now finally, we also put in a antenna on the cathode and took a look at, is there any RF generated? We wanted to see whether RF was being in these coils. And it turns out that here's another case where we had put in the Raney nickel, but we had two big hits right here. We had this RF detection system running, so a spectrum analyzer. Okay, and in detail, there was 43 kilojoules in this one and 35 kilojoules in this one. And here shows a kind of waterfall plot of time of day versus frequency from 0 up to 5 megahertz. And these two signals occur exactly contiguously with the excess heat events, and this is around 500 kilohertz. Okay. This shows that the timing, they coincide with the heat pulses of the timing of it and what they are. And they're not small signals. I mean, they're not huge, but what this is proof of is that this cell, this electrochemical cell, is putting out high frequency RF. And this is not in the literature at all, is that you get high frequency RF. And we've gone up above 5 megahertz. We've seen things up to into the hundreds of megahertz. And we haven't gone higher. It's kind of hard to go higher, but we would like to go even higher to see what we can find. And in the literature, you'll see kilohertz at most of some process on the surface.
This is only during excess heat generation?
It's only during the excess heat generation. That's when it turns on.
I've worked a fair amount with Raney nickel catalyst, and there's various oxidation states. I mean, we had to order a special type of catalyst in oil to make sure its oxidation state was preserved and everything. Did you analyze the Raney nickel before and after to make sure it was in the exact same oxidation state?
Well, the Raney nickel, I don't know if you've noticed, but the Raney nickel, yeah. I mean, you can't really find it. Some of it drops to the bottom. Some of it will get swept and get on the cathode. That's what we think is going on. And remember, cobalt and nickel are magnetic. And we've tried other things, but it seems to work best. And not the first. Crevens and Lutz pointed this out years ago, that magnetic additions seem to improve their chances of getting this. So looking, we'd have to find the Raney nickel if it's still Raney nickel.
So you have not excluded the possibility that the Raney nickel has just changed oxidation states?
No, but I mean, if it did, so what? It's not enough heat. Even if you oxidize it, it's not enough heat to account for any of this by any means. You could get maybe 100 joules out of burning what we put in there at most. Yeah, and we're measuring many kilojoules. Yeah.
Do you have any data that shows what the approximate loading of the palladium or metal is with your deuterium?
Well, I mean, you have to make decisions sometimes, and trying to run a lot of cathodes and hooking them up to get that system to work every time, they threw that away. So we do not know the loading. That's something that would be of interest to now implement back into these systems, now that we have this going. But we do not know, and if we knew, maybe that would be the difference between the 10% reproducibility and something else, but we don't know that right now. So Okay, so now the morphology, we've found a lot of commonalities between the morphology, the ENEA, the morphology we find on these samples that find excess heat, the morphology that Energetics has found, and you always get this funny cauliflower-looking, fractal-looking, nano-looking deposits. Some of it's alumina, some of it's lithium aluminate, and it's not well characterized. It's often friable, so that when you pull it out of solution, it will come off. And what we find is deep grain boundary grooving, up microns of a very thin grain that might be 10 nanometers wide and microns deep. And you find deposits decorating the sharp edges. The deposits go over what you might expect, where the electric field might be enhanced, but you see sharp edges around these grains, and you see the deposit there. And so, yeah, we often see a fractal, small grain size with deep grain boundary, fractal surface generated. Probably there's chemical or electric field enhancements at these sharp edges. What you have is a very uncontrolled deposition system. How to gain control of it is a subject of debate, but it seems that you get these surfaces. If you have a shiny piece of palladium and it's shiny when you pull it out, you know, or even when you put it in, you won't get this effect. Okay, so anyway, the trace impurity analysis of old and new palladium caused us to focus on this alloy, which made a big breakthrough. Chemical additions to the electrolyte increased the probability of seeing this and shortened the electrolysis time elapsed before the events initiate. A lot of people, and Eric can contest to this, will run a cathode for months. We didn't want to wait that long. Unfortunately, this improves we never run them more than a week now. And this seems to improve it. Now, an impossible rationalization of that is that in the systems that run a month, you're not adding stuff in, but it takes stuff off the glass or off the walls or so on and gets the right deposits. It just takes longer to do it, and then you see the effect. That's just a rationalization at this point. So anyway, the large amounts of excess power are real. They're not an instrumental artifact. And, you know, you really have to say it's astonishing. To wake up to this, as many people have over the last 20 years, would say, okay, what is going on here? It's really, really fascinating to try to figure out what's going on. And we're confident. So anyway, the improved electrochemical design eliminated shorts to the ground. The implementation of cell diagnostics, internal cell temperature, voltage, and current measurements eliminates the RF. They're all consistent with it working. We observe weak RF generation during large events. Many attempts to crash this system to make it do this, to try to take the electronics and make it put this power in there by putting RC circuits in, shorting things, anything you can think of. We never could get it to come close to doing what we saw here. So the next step, for us anyway, is to try to get this published in a well-rated journal. And that will be difficult. It will be very difficult for two reasons. We don't have a model. Most papers you like to compare with a model. And we don't have good reproducibility. Yet we're going to try. We're going to submit this to some places and see if we can get this published. So anyway, that's I think what I wanted to say, and the 3 points were the transmutation is really suspect as far as I'm concerned, and just think of it. If either you found evidence of transmutation or you found a lot of radiation coming out of one of these things, then it's nuclear, no question about it. So they're very important measurements to prove, but I don't think they're proven at this point. So we hang our hats mostly on the heat, the electrochemical experiments. It's real. The gas is in flux. There's probably something there. I don't know, but these are the general conclusions that I want to leave you with. And but I really welcome Skinner to be another good laboratory working on this fascinating effect, and hopefully together we'll finally get to the bottom of it. But anyway, thank you. Yeah.
Rob? Well, just to discuss prior terminologies, I really like calling this the Pond-Fleischmann's effect or the anomalous heat effect, because clearly you're showing something that's maybe 100 to 1,000 times greater than what could be described by a chemical reaction, a known chemical reaction. But if this were DD fusion, it would be 10 million times stronger.
Yeah.
And so the fact that it's 1,000 times greater than chemical is certainly intriguing and exciting, but it certainly doesn't show it's in any sense related to fusion.
Right.
It doesn't imply a nuclear process, it implies an unknown process.
Go ahead, Peter.
Well, this is completely sort of just a footnote. I wanted to offer a little anecdote on how to publish papers for things which you don't have very many
Good.
things. And it was when I was on a nano sabbatical in Norway, and there was a guy that I don't want to go into the details why he did some of the best physiology measurements on reindeer, how their nose operates and all that. This was in the 1970s, early 70s or so. And he had 2 reindeer that he had measured, submitted it to the Journal of the American Physiology, which is one of their prestigious things. It was sent back and said, well, if you have 10 or 20 reindeer, we'll consider that. And then he just wrote, and he just wrote back, well, he will do that if the United States first demonstrates that there was not just 1 or 2 people on the moon, but a whole bunch of people on the moon. If they redid that, then he would actually reconsider that. And in 2 days, he got the paper accepted.
No, I don't think that would work here.
I know.
Yeah, Eric.
Few points. First of all, with regards to transportations, I do agree with you that we have to be very careful, and in fact, we have been together with Rob in South Korea, and when David Nagel conducted, probably David Kidwell reported to you, he compared the results of Mizuno that you presented with the results of Miley, and he found very nice correlation between the very huge spectrum of elements which have been found in 2 experiments independently. And David Kidwell, at the end of the lecture, the presentation, stood up and said, this is exactly a picture of dirt. So we have to be very careful, in spite of the fact that and if it's there, definitely there would be correlation between the 2 independent results.
Yeah.
So we have to be very careful. But on the other hand, I think you heard from John Gall very interesting results.
Yes.
And that has, of course, it's just preliminary work,
And it's
which was done.
and it's
But it was
exactly
done
the
very
kind of
carefully, and you will hear about that tomorrow more.
Yeah.
You will be in the reactor.
Yeah,
You
and
will
that's
meet David Robertson, but it is very.
And that's exactly what you need, is people coming at it from different directions, trying to nibbling around the edges to try to find out what's going on. It's what it takes, maybe a national effort, as Jan Kucherov said.
And the second point that I wanted to mention, David Knies asked me when we got our exocysts if we measured RF, and of course we didn't, because we didn't think about it.
Right.
And it is very, very intriguing to look for RF while you get exocyst. And he mentioned, Dawn mentioned during her presentation, also in South Korea, that she got RF only in events where there was a sharp burst.
Yeah.
If there is a slow increase of exocyst, then you don't see the RF. But then I asked what happened, I mean, if they have full correlation between, with regards to appearance, between the exocet and the RF, and David Kidd will say we didn't have, it wasn't, the data acquisition was
Two different
not
clocks.
at the same
Yeah.
pace
Well,
for both, so that you really don't know what caused what.
right.
Is it?
It's within a second or so. Yeah, I mean, they weren't running on the same clocks. Huh? That's right. We don't know that. Yeah.
Just a more general comment too. I think since 2010, there's been a heightened awareness that nuclear processing condensed matter systems is more ubiquitous than we thought. And it goes actually back a little bit before that. But in 2010, with the Fermi satellite, they saw these gamma ray burst activities associated with positron emission from thunderstorms. And no one thought that a thunderstorm could create antimatter prior to that time. Now, after about 1,000 independent observations, there's no doubt in anyone's mind. And I think one big aspect of this is that we so often assume like a Gaussian normal distribution, where a system driven far away from equilibrium is going to have what some people call fat tails, or a transition to self-similarity at very, very high deviations from the mean. And that fundamentally changes your intuition about rare process. And I mean, it's not to say that this is figuring it out, it's just to say that we have been fairly naive in terms of our application of statistical inference to systems driven far from equilibrium in the past. And as another example, again, going back to work that was done at UCLA, piezoelectric fusion between DD ions, hot fusion, has been confirmed in Seth Putterman's laboratory. And again, earlier today you saw some data that was taken by Mark Prellis that suggests that hot fusion in deuterium and titanium that's shock heated is a viable hypothesis. So the point is, whether it's an unknown process such as you've discussed here, or whether it appears to be a known nuclear process in condensed matter systems, both have a significant implication to many things we do, from neutron sources for radioisotope production or diagnostics, to applications that may someday be relevant to energy science.
Another example that I just became aware of is a number of work over a number of years, a lot of work over a number of years by an Italian group who has shown isotope anomalies along fault lines in the Earth. Yes. And which is probably this piezo fusion thing. When you get an earthquake and it cracks, you can get acceleration and get nuclear processes going on, and it makes sense now in view of all this. So there's a lot of interesting ideas out there.
When I gave this banquet talk at ICCF 17, I mentioned this work on that you've mentioned in NRL as clear evidence of some unknown process, and then piezoelectric fusion confirmed, deep nuclear process and thunderstorms now confirmed. Those, I think, are beyond the point of a rational scientific doubt. But then, when transmutations, I also include question marks. Another thing that people have been pointing to is the production of tritium from deep Earth sources. Tritium, of course, has slightly over a 12-year half-life. But again, we know neutron bombardment on lithium produces tritium. I doubt if there's that much lithium in the center of the Earth, but quite frankly, I haven't been there to check it out. So you know, in other words, I think there are some alternative hypotheses that would describe tritium generation from deep geologic sources. But nonetheless, it seems like a plausible hypothesis there could be something.
Yep, that's right. And sometimes it's helium-3 imbalance too, I think.
Yeah, that's another one, exactly.
Right.
But I mean, it's interesting. Yogi Berra had a great quote about, I guess he was mad at an umpire, but he said, look around, you might see something. I mean, it's remarkable when you don't disregard empirical things that don't agree with what you're currently thinking. It's amazing how nature can lead you to a lot more fascinating effects.
Right. Well, and I think, you know, Missouri is well equipped to attack a number of these questions, and I look forward to seeing you make a lot of progress in this area. Yeah. Any more questions? I don't know, did I convince you of anything?
Yes, you did.
Yeah, that's right, okay.
Dick Darwin thinks a lot of this is pretty crazy. And so when he and I talk together a lot, once a year we spend a week together. And,
Yeah.
And he's accepted my invitation to come here. And for anyone who's at all opposed to this, I mean, I completely understand. And I welcome all the skepticism the world has to bear. You know, I mean, the point is we're not out to prove anything. It's just after you've disproved many things, you're still at a question as to what it might be.
Well, I harken back to my group, and especially David Knies and David Kidwell, because you know, if they can't figure out what's wrong with this, I don't know who can. They're great scientists, and they question everything, they understand everything, as well as, you know, and so I have a lot of confidence in them and myself that something's going on here, and that's why I got started in this. I thought there was a pony in here somewhere, and I think there is. And it's just a fascinating thing to be working on at the present time.
I was wondering, since you spent considerable time talk about the gas loading kind of experiments that
Yes.
have been done. Since, as you know, we would like to sort of do some of these things in my lab, and is it fair to say that in regard to an earlier presentation that we saw this afternoon or around lunch, you suggest that palladium that has a lot of defects and cracks is a better candidate for a sort of an interesting event, or was it the other way around? And the other question I really wanted to ask is, if you could sort of just direct from the director's stool what kind of experiment you would say should be done to shed more light, like, you know, do things under more controlled circumstances or with different materials or whatever. Would you have any specific recommendation at this time?
Yes. Well, let's see. Let me start with the electrochemical. I mentioned a little bit earlier, the thrust of the NRL work now is to be Edisonian, try to run 10 or 100 cathodes at a time, because this is so many parameters, to try to systematically go through more parameters to increase the reproducibility. And unfortunately, it's guided Edisonian work at this point. And Tony Lagata in Padua, Italy, is setting up 100 cells to run them. I think you guys are going to be running some. Italy's going to be running some. So if that's going to be coordinated to try to figure out, okay, how can we get the reproducibility up? That's number one. To me, the most important mechanistic experiment to do is I believe something must be coming out of these cells. Maybe it's only RF, but something must be coming out with all this energy. And pretty much gamma rays and neutrons have been kind of vetted, energetic ones from normal nuclear processes. The cathodes we pull out have no activation. Okay. But something must be coming out. So what I set up there, and they're struggling with it right now, before I left, was we bought a bunch of silicon nitride membranes. They're very strong. You can get them 500 angstroms thick or 50 nanometers thick. We want to put down palladium in the beta phase on it and do electrochemistry on one side and put X-ray and infrared and all kinds of detectors on the other, because that lets low energy things get out. And to see, okay, and it does two things for you. First of all, if you get an event, you'll be very sensitive to it. But, you know, our calorimeters are at best at the moment a milliwatt, or, 1 to 10 milliwatts of power. If you put an X-ray detector in front of something, your sensitivity goes down to picowatts or better, right? I mean, so suppose whatever this process is going on all the time, just you can't see it at 1 and 10 milliwatts. Well, that detector would tell you right immediately that there's a lot of counts coming out. Maybe it's a picowatt of power, but it tells you what a mechanism is. So they're set up. They have Jinghao He has made a cell or two that will accommodate this, and so I would encourage Shubra and her group or so on to figure out how to lay palladium down in the beta phase and ship it to, I mean, it's a way for you to get going. Ship it to them so they can do this measurement and see what goes on and collaborate. And to me, that's a mechanism, in the electrochemical side, that's the number one mechanistic experiment to look at. And I am interested in low energy X-rays, betas, or maybe even alphas won't get out of these cells. So, you know, maybe it's still energetic, but it's alphas. And you'd find that out. I'm interested in infrared, especially around phonon frequencies of palladium hydride. And you could do that with bolometers and filters and so on. You could find out if there's any spectroscopy to be done, if it's not just black body, if there's any lines in that infrared that's coming out. Those are important experiments to try to do right now. Yeah.
One thing, there's been very little study of what the hydrogen system's doing under the loading of the metals. So what we heard from Helmut earlier today is that these neutron diffraction studies could tell us about physically where the hydrogen's going in the metal.
Yeah.
We don't really even know that. I mean, we have some assumptions, but we don't know if this is going into cracks and voids and faults in the metal, or whether this is becoming more uniformly distributed in the metal. And of course, between nickel versus palladium, you'd expect a difference because palladium is much more permeable by hydrogen.
Right. Okay, yeah, go ahead. Now, one of the problems I have with that is these are more morphology. I mean, if these are more morphology pictures I had put in. If you want to take a closer look at them, you can. Where was I going with that? Yes and no. Hydrogen likes to go into palladium, but if you're looking for the hydrogen at green boundaries or in clusters or in a, you're probably not going to see that because it's going to be less than 1% of the hydrogen that's in there, and it's going to be swamped in the single. Now, if there's another phase that comes in, if it goes into the octahedral or tetrahedral site or something, you know, a significant amount jumps up there, you'll see something like that. Because, but you know, you've got to have some within 10% or so of the two different things you're looking at in order to pick it up, or maybe 1%. Isn't that true? And I think that, and that's one of the problems with those. I suggested some of these experiments years ago, in situ neutron scattering. This is from a 2007 paper. But there are some nuclear. You guys are nuclear, some of you. Yeah, this one I sort of liked. And you can pick your system, but let's suppose now we think this is on the surface, right? Let's suppose you ion implanted some isotope into the surface, or you diffused it in, and then you activated it with neutrons or protons or whatever it makes sense to activate it, or activate it before you put it in, and diffuse it in just into the surface. And then you load it up in an electrochemical cell, and you look at the decays, and you do things to it. You put magnetic fields on it or something. Is this such an unusual environment? Am I altering at all the lifetimes of these states, the decay? Am I altering these decays? Because if this is some kind of an unusual environment, which I think it is, a very high electromagnetic environment, can I alter at all the decays of something like this? So you're putting nuclear physics into the problem and saying, is this unusual, way out of equilibrium material doing anything to my nuclear physics, rather than trying to figure out, well, what is the solid state doing to the nuclear physics? You can find out, well, is there some evidence here that it is doing something to the nuclear physics? So I kind of like that. You guys have the isotopes, and it's you know, measuring lifetimes is pretty easy. The other one would be, you know, in situ Mossbauer with a similar idea, although these are tough. These have the same problem I mentioned with the neutrons, is that if only a small fraction of your radioactive isotope is experiencing this unusual field, you won't see it. But on the other hand, if you just diffuse it into the surface where it's probably happening, you might have a chance of seeing something. So that's a search experiment. And perturbed angular correlations, I don't think you guys do that here, but it's again, just another way of looking at the environment that you're putting these putting these in. And these are sophisticated.
Of lifetime decay, that would be easy to do.
Yeah.
Huh?
That would be easy for us to do.
What?
To see if the half-life decay of
Oh, yeah, right.
198
Right.
is different because it was in that system.
Right. They're pretty accurate. You can get pretty accurate count rates as a function of time out of them.
And perturbed angular correlations is quite easy too, because there's this area at ultra low temperatures called nuclear orientation thermometry, thermometry, and the same apparatus would be required to
Oh,
do
really?
this.
Okay.
So there's been as much as there's any industry at low temperature physics, there's been hundreds of apparatus for nuclear orientation thermometry developed at ultra low temperatures. So the point is, those are around.
Yeah, I got these little pictures off the University of Washington website. They still have an active perturbed angular correlation program there. And there may be a few other schools, not many left, but there's a few other schools probably that do have it in the U.S.
If I could too, I think this is really, valence fluctuations are a fascinating aspect as well, because to my knowledge, palladium is unique in that it exhibits what's called the Stoner enhancement of paramagnetic susceptibility. If you look at nickel, that's clearly S2D8. If you look at platinum, it's either S0D10 or S1D9. But then in between, palladium is right at the point where it's kind of ambivalent energetically about whether it's S0D10 platinum-like or whether it's S2D8 nickel, slightly magnetic. And so you get this enhancement of paramagnetic susceptibility when a magnetic ion is placed inside the palladium, called Stoner enhancement.
Right.
And that's really well established. And the point is, timescales, these fluctuations in valence occur maybe on the order of a picosecond, 10 to the minus 12 second. Whereas if there is anything nuclear going on, not saying there is, just as a hypothesis, then the nuclear will be complete in about a fraction of an attosecond, 10 to the minus 18 seconds. So the point is, people have not been considering valence fluctuations, which last an eternity on the scale of a nuclear process. So,
well, in fact, what we are examining now is possibility of electronic phase transitions, which would be faster yet.
wow.
And it's been interesting looking at that, I have to say, at the moment, because you can get up to 10 to the 15, basically, with electronic phase transitions.
Right.
So. Because from our X-ray work, and you may find this out with neutron scattering too, but in the X-ray work, looking at the palladium sublattice at high loadings, we never saw any structural phase transition at the high loadings. Not saying that, but we insensitive to the hydrogen though, of course. So, yeah.
Finally, I think that one thing that plagues this area of study is that people don't just, as you've done, show the empirical results and say, well, I don't know what it is. Too often people throw out a straw man theoretical idea. Many times those ideas from what we've heard are completely bizarre. And that focuses everybody on these completely bizarre ideas instead of on the empirical evidence that our understanding's incomplete.
Well, of course, we speculate all the time on what this might be,
Yeah.
but we don't
publish
talk
it.
about it or publish
Put it
it,
on the
and
website.
so only talk with certain people or something. Don't want to embarrass ourselves.
Likewise. But if we stick to empirically what's reproducible and what experimental
Yeah.
reproduce.
Right.
This is very expensive.
It is.
Not this, and so you are lucky that DETRA is funding your program. How can we be lucky and get some funding from the Department of Defense to expand our studies beyond what we're trying to
Well, what I've been
achieve?
told, if somebody, maybe us, gets a paper into a good journal, that might then free up the funding agencies to add some kind of BAA line to accept proposals in this area. Now, DOE has paid lip service to that. They said back in 2004 they'd accept proposals, but they've never accepted one. I've sent them a couple and they've rejected them. That's not unusual for the DOE to reject something to DOD, but so it might be other reasons for it. But that's one thing. And the field is changing. Rob, I was supposed to go. Rob went to Brussels in July, was it? Several people went in this field and they listened to him in the European Union, European Parliament.
The European Parliament in Brussels, and we're actually in the base plan for material science development in Europe. So
exactly.
So the planning documents.
So for the European Union, there will be a line, if you're looking through there, you're a researcher, there's a line there that says they'll accept a proposal for this area. That's what we need here. I know in NASA, there's a growing interest to have this field brought more to the fore, and they may lobby for us to do that. So, you know, I think the climate is changing. And in this sequestration environment, I don't know how that'll ever happen, but I think it'll break. I don't know, in the next year or two, there'll be a break where they'll be either forced to fund this because somebody came up with a really good answer to this, but funding is extremely important, and we were fortunate to. It took a lot of work. I mean, it took me several years to beat on these guys to finally get to support us, but. And they want to continue supporting it, but they are getting big pressure from above to not do it. So they're fighting for us all the time, fighting their upper management to try to fund us. Every year, as they've had to fight their upper management to fund us. So it's whether in FY13 is up in the air right now regarding that funding.
Peter Pfeiffer pointed out earlier today that sequestration has a double entendre.
Yeah.
It's sequestration of budget or sequestration of carbon. So it's sequestration, double entendre.
So, I mean, I thank you for listening, and I hope you got something out of it. And,
yeah, thank you so much, really.
Very nice.
Yeah, well done.
And I appreciate any questions, any skeptical questions I can answer, let me know. But keep in mind that NRL didn't come public with this until a few weeks ago in Korea. Right. So this is pretty new to the community. The community, in my opinion, probably went ho-hum because they said, oh, we told you so. Why'd you spend all that money in 4 years to find that out? We already knew it. But you know, I think an institution adds a lot of pizzazz to it, and hopefully it'll help the situation change. So.
Also, the careful discipline. It's really
yeah. So.
Thank you very much.
Okay.